we can slowly start. So what I want to do is a repeat thing, and it is my intuition that what is done here is extremely important. Okay? For quantum field theory and further developments in quantum field theory, including possibly quantum gravity. This is my, it's only an intuition. I'm not an astrologer, but it looks like that is the case. So, why do I think that? What you find here in this demonstration is the quantization of the entire Weil algebra in all compact regions, all what they call partially complete regions, which are compatible with causality, or for example, the ring limits. This gives a prescription for quantization entirely from Wigner's work on the Poincare group in terms of this irreducible representations. Okay. This is quite remarkable, and I realized later on that this also covers one case, namely the continuous spin, what is called continuous spin representations, which cannot be handled by standard quantum field theory at all. There are proofs that it cannot be done. But this technique that these people are proposing also accomplishes that. It only uses the representation theory of the Poincare group, starting from Wigner, and along with course of the calculations, it ends up by proving entire compatibility with causality. At the very end, I will try to put some speculations. This is whole thing is done for free fields, but I will put forward a speculation on how it can be extended also for interacting fields. But it is really a speculation. I don't know whether my suggestion is correct or not. But,
so can I ask a question?
Sure.
No, so just to understand, is this an attempt to make field theory more rigorous?
Sorry?
Is this method supposed to be more rigorous than the usual field theory methods, or is it more general?
No. The main advantage of this method is that it does not use expansion, it doesn't use quantum space at all. Let's see. So it doesn't need the reason. But for field fields, well, you know that from massless field fields, it's a problem to quantize massless field fields for higher fields. There is this Vassiliev thing and all kinds of things. And what does not have, if you start with a Lagrangian formulation, one gets into all kinds of constraints, and one does not know how to resolve those constraints. In canonical quantum field theory, this one note. Here, no such problem arises. You have an explicit quantum field theory, regardless of spin, and including the one case which has been totally excluded by work by other people, especially, that there are no local fields. So I would say, on one side, it's conceptually more powerful, on the other side, it actually covers cases which cannot be covered by standard quantum field theory, even before field. So that's what I would say. So this should be known to anyone who's involved with quantum field theory. It's not rigorous in the sense of using theory mathematics. That is not the case. The math is quite I would say elementary. It should be elementary, let us say, for all practitioners of quantum theory. It doesn't involve maybe stuff on pure space or Poincare algebra and stuff like that. But totally uses the Weil algebra. So I wouldn't say the maths is heavy, but the results are, I found them startling, because even CP, causality emerges from CPT. This was shown already by long ago by Bisonian and Wickman, but their method is a special case of water interest. So that is my feeling. The feeling can be revised, but uh, definitely it transcends the standard case theoretic techniques. Okay. So I will start. I will start by considering tensorial fields. Okay. Just to be definite, what do I mean by tensorial fields? The irreducible representations that you write the tensorial fields. If one looks at 2 pi rotations, it is one. Okay. Tensorial means that is an intrinsic characterization of tensorial fields, namely 2 pi rotation is plus one. This is Raphael Sorkin's tensorial representations. This is Raphael Sorkin's and Friedman Sorkin usage, and it's a very appropriate language because it doesn't tell you about spins or anything like that. Simply says that with these representations, 2 pi rotation is plus one. It also applies to quantum gravity. So we start with the representation of the Poincare group. I'll call it P plus. So all Poincare transformations whose determinant is plus one. Okay. So it involves all these proper Lorentz transformations, whose and rotations, but it also involves the CPT operation. Okay. We need CPT. If for some reason CPT is gone, this proof also goes. Okay. But if CPT is gone, we can discuss it also. Many other things will go, including there will be a lot of trouble in formulating scattering theory. In ordinary standard quantum theory, you don't have CPT. There is immediate problem of how to write S matrix and how to write the Lemon-Simons formula for scattering. So we will assume CPT. Can CPT be broken? Yes. It happens because of it can happen. It does seem to happen because of infrared effects. But how do you formulate scattering theory in those cases? Taking this, breaking into account, I have no idea. It doesn't happen in the vacuum sector, but there are other sectors of QED where there are infrared clouds which cause trouble. So how do I do scattering theory? I don't know. It's like an open problem. So what I'm going to do is to take the direct sum of 2 representations. Namely, I take the vacuum representation where all the rho representation is called rho is a mapping from the algebra or the Poincare group into linear operators in some Hilbert space. So rho is a mapping, and we consider those mappings. And vacuum sector is one where all the elements in the group go to identity on the vacuum. Okay. So the vacuum sector is spanned by the vacuum multiplied by any complex number, and we will assume in the standard way that the vacuum is normalized to 1. Okay. But since I don't determine it to be plus 1, there are elements, there are all elements of the matrix, the element minus 1, because we are in 4 dimensions, the element minus 1 is in the Poincare group, and this reverses all coordinates, and it is called CPT. And we know that it is represented by anti-linear operators, anti-unitary operators on the Hilbert space. That is also quite important. Okay. So I will denote the anti-unitary operator later on by theta. Since I have this RTF to backside this, there's no way I can write theta. I didn't use the text. So by theta I mean CPT. Okay. Now we started the elements of the Lorentz group, and take any the Lorentz group is acting on space-time. So that is already the moment you say Lorentz group, it acts on space-time. Okay. If you have no space-time when you say Lorentz group, but you give me the group, then one of these homogeneous spaces is space-time, whether one likes it or not. It doesn't require quantum fields. It's acting on space-time, and among this Poincare group elements, there's one element which is non-compact in the Lie algebra sense, which I call K1. Okay. So we take a canonical basis for the Lie algebra, namely the 3 angular momenta and the 3 three boosts, and there's a Cartan killing form, there's a bilinear form to normalize these operators. So we say that the scalar product of the two J's is something in the 4x4 matrix representation, and the J's act on the case by rotating the case and so on. So you pick any element, it is not compact. So there's one element in the 4x4 representation is not compact, and whose normalization you can get by using the Cartan-Killian form. I assume that you know what is atom you knew. The Cartan-Killian form I assume you knew. Okay? So we can pick anyone, call it K1. It doesn't matter. You pick anyone and call it K1. Okay? Given this K1, small K1 in the Lie algebra, there is also the element. So the K1 is acting on space-time, and it has the property that it necessarily link to the axis invariant. So if it's in the 0-1 plane, it will do so. It will give two directions in four. It will have in the orbit of its action on space-time will have two directions which are invariant. Call them 1 and 2. Then the orthogonal direction I'll call 0 and 1. And this K1 is acting in the 0-1 plane by in the Riddler language, describing a constantly accelerating particle. So you can, there's a convention, choose that plane, then there's a 2-3 direction, and I can talk about 2 pi rotation around 1, okay? Or pi rotation around the 1 axis, and it will reverse the sign of 2 and 3, and it won't do anything to 1. So I call that pi rotation is G pi. Why do I want to do that? The CPT operator, which I call theta, will reverse the directions 2 and 3. Okay? Direct all signs 0, 1, 2, 3 reverse, but it also will reverse 2 and 3. I don't want to reverse 2 and 3, so I take a pi rotation around 1 axis, which reverses the sign of 2 and 3, and I will multiply K1 I'm going to sorry. So let me keep this in mind, okay? And I am going to do the following. I am going to take this theta, this reversing the sign of all the coordinates, and multiply by G pi, pi rotation around the 1 axis. This will reverse the sign of only 0 and 1. Okay? So what it will do is to take the Riddler wedge, that is this T sign 0-1 plane, in say where 1 is increasing, the coordinate 1 is increasing, say on the right, and it will map it in the left half. Okay? So it will simply take one Riddler wedge and take it to the complementary Riddler wedge. Okay? So the reason for putting the pi is I don't want to do anything to anything. So it is just taking one Riddler wedge and going to the complementary Riddler wedge. Okay? I think I told last time that they take one Riddler wedge, and I asked what are the space-like components, space-like points related to this wedge. It is this other wedge. Okay? All the points in the other wedge are space-like related to the first wedge. So this JW geometrically is taking one wedge and mapping it to the causal complement. This is the operator that Dickman had considered long ago. Okay? So let me do that. Okay? Let me take that. This is another problem. Okay? Since they boost the acceleration only on the 0-1 plane, and it is it will commute. So it is acting on the 0-1 plane by conjugate to matrix, but this operator is -1, -1 in the 0-1 coordinates, so it will commute with the boost. So this is a very important property that this operator commutes with the boost. So the boost, give me K1 and a corresponding boost, which is this 2x2 matrix cos theta, shin theta, cos theta, and 1 along the diagonal elsewhere. This will commute with that operator. Okay? So giving one boost, I pick out 2 Riddler wedges, one on the right, the second the causal complement. So this is going to be quite important.
G of pi rotation.
G of pi is pi rotation around the 1 axis.
Why should it come?
No, I consider this operator. No, this is not the boost operator. This theta
You're saying it commutes with T for IT cable. I'm asking why should the rotation of this problem?
Because the boost operator in the 0, 1 plane is 2 by 2. So in the 0, 1 plane, this pi rotation around the one axis will not do is pi rotation around, so I can say the word. Pi rotation around the one axis is 1, 1 -1 -1 along the diagram. Okay. In this, I rotate by pi around the one axis, so it's -1 -1 in the two things. Okay. So, but the theta, the boost operator is 2 by 2 in the first 2 by 2 block, where this pi rotation is +1, so they come in. The product will be the same. So this operator JW takes the linear wedge on the right half and maps it to the left half. So they are causal complementary. This is the operator that comes directly in your algebraic in the definition of the Lorentz group. Okay. Give me the Lorentz group, I can do this. Okay. Give me some other group, maybe I can do similar things. For example, for the digital, I have not can do this. I don't know whether there is a CPT operation in boost in for the digital group. I have not had time to check. And Pastor pointed out that in other dimensions, say 3 + 1, there will be immediate trouble because in 3 + 1, what will you do? I mean, it's 3 basic matrix. So, what will I choose to bring back CPT? What is the causal complement of the linear wedge in 3 dimensions, 2 + 1? I have not checked. So there might be trouble. There may not, this kind of activity may not go through or may require modification. It requires, can be checked. I don't have time to do this. So I think it's a very interesting issue because the whole thing is intrinsic. Okay? I am not pulling things, pulling this like quantum physics. I am not doing anything like that. It's purely geometrical.
What is the actual
CPT is what we call P. It's a reflection to CPT. C is added on for good for luck. CPT reverses all the coordinates in 4 dimensions. Okay. And it has a property that is determinant is +1. Okay. In 4 dimensions. If you take odd dimensions, it becomes -1. So we have to check whether, because it is -1, do things go wrong? Okay? I don't know. Okay? Is it existing in the DC space? Seems to me no, because I think what will happen is it will map a spatial region. Well, some of you would know that there are causal horizons. There are horizons in DC space. And I suspect that if you do this kind of operation, it will take you from one side of the horizon to another one, which you cannot access. And since the horizon is observer dependent, I don't know what to do. Digital horizon is observer dependent. It depends on who is looking. So presumably the CPT will, whatever if you manage to define it, it will depend on the observer. Then I have no idea what that is. It has to be analyzed. So I don't know whether this analysis of Lobkowitz and Celestia and Bennington will go through. I don't know. For this purpose.
So what does C do? C, the charge conjugation. No, what does charge conjugation do with this? What has to complex conjugate a field? What does it do here?
Can somebody explain what this is? Charge conjugation is not defined. CP is what we call P. These people simply notation.
Okay.
Call it CP as a P is not there. So CP is P.
Okay.
But it's anti-unitary. No. CP is unitary. T is anti-unitary, so CPT is anti-unitary. It is that operator, CPT is that operator, for which quantum field theory has proofs that it exists in all local quantum field theories. See, nothing is said about C. C separately, nothing is said. No commitment is made. It's not necessary. CPT, this operation which reverses all coordinates, is necessary. So you simply take it as an operator. But what about pi rotation? That is more problematic. Is rotational invariance absolutely essential for quantum field theory? I don't think so. Then what happens if rotational invariance is broken? No idea. This analysis will not go through. So there will be trouble to quantize objects where rotational invariance is gone. And this I am reasonably sure, even in quantum field theory, but where it will bite you, I don't know. Okay, some work has to be done. Okay, so CPT is that called theta. I think that is the correct notation. In the quantum field theory, the operator CPT is normally called theta. That's what Schwinger does. They are called theta. Yes. Okay. So now the small JW, this geometrical operation, is represented by a capital JW as an operator on a Hilbert space. Okay. I will get the Hilbert. Where is it acting? It is acting in the representation space on which the representation rho acts, which is a direct sum of one particular Hilbert space for the particular spin I have chosen and the backward. Okay. So this is an operator in that representation space where this operator will be anti-unitary because it is an image of the theta of the CPT operator. We call JW. What you can call it? It's not theta. It's theta times pi rotation. And I will similarly take the representative of K1, small K1, whose rotation, whose the time translation as the expression I do capital K1. So this is the operator in the one particle backward sector of the boost. This is the operator which is the product which acts on the Hilbert space consisting of CPT and a pi rotation. Now, the JW square is identity. This is purely a geometrical fact. The small JW square is identity, and in the beginner approach, all geometrical operations should be maintained completely when you go into quantum field theory, up to some phase. Okay. In fact, this one should discuss in the epistemology of the beginner papers. We start this representation of the concrete group by looking at states preserving probabilities under Lorentz transformation, concrete transformations, and he tries to see. So the states to be invariant. So physically, what do we mean by invariance? It means that all probabilities are preserved by the states on the operator algebra. If you make a Lorentz transformation or something, the mean value of an operator and its Lorentz transform to be the same. For the state is not a vector. So how do I lift this state activity? This is activity which I have to do and the state when I go to a moving frame. How do I lift it to a vector, a Hilbert space? There is a whole thing that he has done there. And he shows that the lifting will either give you a unitary operator or an anti-unitary operator. And there could be anomalies. For example, SO3 will become SU2. So there's the Z2 anomaly. That is, you cannot represent, in certain cases, SO3 cannot be represented as a vector state or a vector. You have to go to a twofold covering. So you get a central extension, which we might call equally as an anomaly. Okay. So that proof is underlying all this. Okay. So I am assuming that this operator has an image they call expression IT7. Okay. And JW square is identity. Now, as I told you, geometrical operations should be maintained in quantum theory. But I told you that the small JW commutes with this operator with small k here. So at the capital J level as well, I must have this equation. So this commutes with boost operator. Now this tells something very important already. This one, because of the I here, it says that if I remove the I and look at this operator, exponential minus P I K1, no I, and look at J minus W. This JW without the I, this equation already shows what the I here, that JW anti-commute to K1. The JW is anti-unitary. So it should match this operator to plus here. Not the minus will become plus. This is very important. This change the sign here is very important. We will see later that this condition, when I start analyzing later, that gives you this what is it? The fact what they call a Kubo-Martin-Schiller condition in statmic. The statmic partitioning function, the given state, they go into the complex plane to a strip in doing things like the Young theorem of zeros and so on. We will see that the basic condition is underlying those forces. So I come to this equation coming from here, and I will actually derive that analyticity in this strip on the KMS state as we go along. Now, for the present case, there is another important fact. Given this thing, I can define an operator say called SW. I define an operator called SW. What is it? It is JW, the input space, which is delta. What is delta? Delta is the operator, and delta to the power of half is this operator. Why the half is put in conventionally, and we will see some reason why it is maintained by people doing algebraic fundamental algebras. This notation is retained by them. So there is a half here. This operator defines the half, okay, delta to the power of half, and then we define this capital SW. Okay. Now, capital SW is what is called the modular operator. Okay. Nowadays, a slew of papers are coming out on this modular operator, especially from ICTS and places like that. With this operator,
Hence, delta of the SW is the total modular of
it's a modular, and maybe this is the this is the operator. Is JW is called modular operator.
JW is called the anti-unitary modular communication, and delta of W is called the modular operator, and SW is the total operator.
Okay, I call SW as a total operator. Okay. So, what is the importance of SW? You see that when I square SW, I get 1. Why? I take this, multiply it again by JW, but JW reverses the sign. From here, you see that JW reverses the sign in front of the exponential. So, when I take two of them and pull JW through, the sign here will get reversed, and so they will cancel. And then at the two ends, JW squared is 1. So you find that this square of this operation is 1. And likewise, JW squared is 1 for reasons I already showed you. Right? Because it's basically CPT operator multiplied by some phase. Some 2 power rotation, it becomes 1. Right? I'm considering, as I told you, tensorial representations. When it is not 1, 2 power rotation is minus 1. We have to go into some other tricks. This won't be the Tomita operator, the spin half, and we will get to do a slight multiplication. Some twist of the standard Tomita operator.
Hence, delta W and JW are not part of the algebra of W.
This delta W are part of the algebra or the concrete algebra over the complex numbers. Okay. So is a part of the Poincare algebra over the complex numbers, but it's not a part of the local algebra.
The delta of W cannot have zero eigenvalue. But
I know that's not correct. So that if you're talking about delta W to the minus half 325, this kind of question you're asking. My you told me this that somewhere that delta W to the power of minus half does not exist. So type 1. So I thought about it and I don't know the answer. I know that this is a correct operator. So what do they do with the zero? When you, so how does inversion define? One has to check. No? So I don't know the answer. I don't know that. So we'll come back to that. But I do know that in this context, they are well defined.
yeah, and if you just polar decompose SW, you will get something like this. And if you take that as the definition, then it's fine. Because there the delta of W is actually inverted. But the way you have defined what guarantees that you want to apply that.
Maybe that is one way of changing the goalpost. So you can change instead of writing like this. I can keep suggesting that this delta W take the adjoint of delta W to the power half, which will take.
Anyway, you can continue.
So I reserve. I will come back to that. Try to think about it and ask somebody about it. But anyway, the important thing is that the square of SW is identity. And it is also JW square. And but SW is not unitary, which is simply is if you look at the this equation here, it's a polar decomposition of SW. What do I mean by polar decomposition? It is broken up into a unity part and something like a modulus. So this is the modulus part, and that is the anti-unitary part. So this is the polar decomposition of anti-linear operator. If you look at SW star SW, you will find that it is delta, and delta is definitely not bounded. It's not a bounded operator, no matter what. So people who try to use log delta as a Hamiltonian are just doing wrong things. You get wrong answers, and if they were correct, we will not be around. The word will collapse because it has no bound. There is no upper bound or lower bound in eigenvalue. And all this is active on a Hilbert space, as I told you, it's a direct sum of the vacuum sector and H1, the one particle sector. Yeah. So here I am just telling you that there is another modular operator is obtained by conjugating. So this is the thing he was telling. I take this SW and apply JW on both sides. So if I apply JW on both sides, I can write this because JW puts a sign on top, but if the sign is very bad in cosmic trouble, I can put it on the other side. That is the suggestion. Let's read this. So the main point is that when I conjugate delta to the power half, I can write this delta to the power half at the left times JW. So, but this is new. So with this is new Lolita operator corresponds because I have done this geometrical operation of J. It states a right relative left relative. This is a new Tomita operator SW, which I call SW prime. So W prime, I mean the causal complement of W. Okay? So W is my right relative, W prime is my left relative. They are causally separated, and SW prime is the Tomita operator for the left relative. Okay? Now, In H, I am also given the Hilbert space. So it is given a scalar product. This is true for any space. It is given, there is a scalar product which is finite. Okay. So what do I do? Or what do they do? They're going to take this Hilbert space, they are going to split it into two parts. One they call real, the other they call imaginary. How do they do that? By real, S is an anti-unitary operator, anti-linear operator. So I will call all elements of the Hilbert space vectors which are invariant by SW as a real. Okay. Why? In the subspace of vectors, I can only take real linear combinations. If I take complex linear combinations, it will not fulfill this equation. So I can only take real linear combinations. So I call this as a real subspace. Okay. And then, any element in the real subspace will be one half of some project, some operator like this at your edge. Because I apply SW, you get back, this is very one. So I apply SW, you get back the same thing. So all these operators, looks like some prediction operator applied to H. Okay? But getting the real part, a real subspace, a particular real subspace of this Hilbert space. Notice that this real subspace is not the same. If you go to the causal complement, the real subspace is something else. Okay? Because the operator W changes. So there is no fixed real subspace that keeps it goes changing. So reality is not reality in the language of the function being real. It is not like that. It is real in the sense that the vector space is a real vector space. So in the technical meaning of real vector space, only it is a module over real numbers, not over complex numbers. That's what it meant. We will see later. At the very beginning, I was hearing text from scalar fields with real text function of x, the coordinate. You may ask, what is the relationship of that real function, which were real in the universal sense? So at each point of the coordinate is giving a real number, and this real surface, and I will show you that surface for real functions, when I take a Fourier transform in the linear range, which I will do for you, which will give you this real surface. So I will define the Fourier transform later in a particular linear range of the real functions of the earlier notation, and I will show you that will produce for you this surface. So that reality and this reality are intimately linked, but that reality will keep changing. The Hilbert space reality will keep changing as you keep going from edge to edge. And the interesting thing is this one, not that one, because we want to avoid activity. So the implicit reality is this one. So I start with this. So now I write the biological. So what do? I will define for each real vector in W. I will associate with an operator which is called YW. Other notation I will use script W. I simply call it WH1. And likewise I call WH2. Then I will write in algebra, which I say that the product of two W's, where let's say H1 and H2 are real, is given by WH1 plus H2, while element of the Y algebra WH2 plus H2 times a phase, which is my exponential minus I over square root of 2, and normalization times the imaginary part of H1. H1 is a real vector, H2 is a real vector. Real in the sense of the Tomita operator, and the scalar product, however, is not the real. Is, as I say, vector being real, the real subspace doesn't mean that the scalar product is real. So, what you get in the definition, you get imaginary part. How is it coming? This is borrowed from what happens in quantum field theory. They think of these W's as coming from exponential I times this scalar field named with a real function. There also I got a case because the scalar two real functions paired together. Some some scalar product. It is borrowed from there. So I will write the while algebra like this. And we need one more relation, a star relation, what is meant by Hermitian conjugation, and that is also borrowed from there. The W of a star is W minus H. So all these things are in the real surface. Yes. So we can think of this W, this while algebra, and the while algebra of the renewed H on the right. Okay. Good. Now I have to tell you what is my how do I find a representation of the WH? Two prime ಮತ್ತೆ ಇದು ಪಾಕಿಂಗ್ಲ hello ಪಾಕಿಂಗ್ಲ ஒரு ஃபைல் வேற ஃபைல் இருக்கு சொல்லுங்க. There is a 2 prime where I completed this picture. Because I extended this node, but I can't find it.
This is the one. This is not the one. Right?
No.
Are you done with this?
Yeah. If you can pull that other one out, it's better. Yeah, it has also been a fair.
Is it?
The title was again addendum, but there's a 2 prime there. No, that's it. It's 2 prime, right?
Yeah.
That's right. Go to the end. That's it. There it is. Fine.
Just a minute. Just.
Yeah.
End or the beginning?
Beginning. Excellent.
This is the.
This is right. So, how do you find the question now is, I need a representation on a Hilbert field of this whole thing. What do I do? The whole problem is this while algebra got exponentials of element of the Hilbert space. How do they act on my Hilbert space? What is the Hilbert space on which they act? The answer is again borrowed from a field theory, but the field theory is a crutch. So we know how in the original lecture I told you how to take a scalar field and carry it to the real function, act on the vacuum, I will generate the entire Fox field matrix or symmetries. It depends upon F and all this symmetric scalar product, and the scalar product and in the Fox place, I get and it is also when I take the scalar product, I get scalar product. So this F will get mirrored in this expression, integration and integration operators. And when I take scalar products, I get some scalar products with the S. So that this equation, there is a scalar, this expression, I can simply take this and copy everywhere, fire there with W of H. Replace F by H. You get an answer. What is the scalar product? Well, you can take it from here and replace everywhere small f by H. You get an answer. That is the answer you want. This is some side thing we are using as a crutch. If you don't like it, you can try doing it directly. But you don't want to waste time, you can simply use this expression, transcribe it to the language of the Hilbert space, then you can forget about it. It's true that as I told you, that these functions here, which are localized in interfaces, will come back later, not in the avatar of fields, but in the version of this analyticity in the plane, in a strip, which will be very important for StatNet. So we'll come to that later. Okay. Now I need your help again. Can you go back to my that local quality physics paper? Here, localization, localization. Here it is.
Wait, wait.
This one. That's it. That's it. What I do, I don't really understand.
I need to share the screen for the online audience as well.
Ah, that's it. Okay. Now, let me again emphasize that the construction I gave you for the representation of the wide algebra uses only the representation theory or the concrete group coming from Bigman. Okay? Because all the scalar products I wrote down are already in Bigman's papers, okay? Including for those who are continuous things. Okay? So they're all there. Okay? So we don't, there is no, I can't see any block whatsoever in writing this quantization for any mass in any scheme, including continuous. This is not the case if you do quantum field theory. Okay? The important thing is, it seems to be transcending the limitations of quantum field theory in this context. So, I think that is something to keep in mind as we keep going. Okay. I also want to remind you now that this whole thing maintains causality. So, in this picture, I am showing you what is happening here. So, in this picture, I am telling you what this JW is doing. You have the right is the rich W in the 1013, and you have the left little rich. This JW is exchanging between them. Okay? So, that is something you should remember. Now, I wanted to show about causality. Remind you about causality. Now, I want to show now that this whole activity maintains causality, which I showed last time. And to me, or to Bisonino Wickman, it is not at all obvious why it is happening. I will show you that this whole construction maintains causality. Okay? The Bisonino Wickman theorem, which is whose free part is this one, proves it for all interactive fields. Okay? Obeying axioms of quantum field theory, and the proof is discussed carefully in the book of Rudolf Haag. Okay? So there's a long discussion on this, and it is indeed a remarkable theorem which connects the Tomita Takesaki theory with algebraic quantum field theory. It was one of the major discoveries which were made around that time. So I remind you what I am doing, how I proved it last time. So I want to prove that the wide algebra in the causal component in W, so W prime is the left edge. So the wide algebra is the left edge. So I change the notation instead of writing y, just script W. This commute is a commutant of the algebra in W prime. Prime is the whole algebra. You look at the commutant, and I want to prove that this is the case. But we showed that in the wide algebra, the product of this element and say, predict the real vector side of it, in wide algebra is the real vector, the Tomita says. And the real vector W prime, J called vector, is defined by this equation times the imaginary part of eta W prime inside W. This is how it is defined. But notice that what I meant by reality, real vectors, the two subspaces are different. Okay? They are not the same because the Tomita operator is changed. So this is not, there are vectors in the same hyperspace. It is huge. Okay? But the subspaces from which I am representing are different because of the fact that the Tomita operator is changed. And I want to show that these commute, which means that this imaginary part has vanished. So this scalar product was not real. How did that happen? Well, and here is the magic of the no. We have only one interface. Only the full concrete group is active. Hilbert is as you know, Hilbert is a separable inbuilt into Hilbert is giant. You can accommodate lots of things, including all the students in the class level. No problem. It's huge. Okay. So only one Hilbert space. All scalar products are given. But I'm picking real surfaces. The point I want to make is there are many real surfaces. And what I am doing now is to expose to you what people call as a real form of the Tomita packet secretary. Okay. That's what Logo calls. I believe that that is what also the Doppler calls. So I want to show that this object is real. How do I show it? Well, first I remind you, for anti-unitary operators, basic identity. JW is anti-unitary. What is that mean? If I take any vector alpha and any vector beta in the Hilbert space, like the data beta and the data beta, if it were unitary, the two JWs will cancel. But it is not unitary. So what happens is this object here, look at it. It is linear in data, but because of the J, it is anti-linear. Likewise, this is anti-linear in alpha, but because of the J is linear. So whatever I write, this what I get out of here is linear in alpha, and it should be anti-linear in beta. So you have to reverse the scalar product. Okay. So this object is theta alpha, and J is anti-unitary. So this is flip of the terms, which as I said earlier, should be called as moving from right to left. As one would do if you are writing in Farsi or if you are writing Urdu or something like that, you read from right to left. So finger, that's what finger calls when you write for correlation functions, the action of security. That's also important for standard grade. So keeping this in mind, let me quickly show you what happens. Yeah. I take the scalar product of some vector eta in W prime in the Hilbert space and psi W in the W space. And because the Tomita here, this SW prime for W prime acting on eta W prime doesn't change it. That's how we pick the real substance. Likewise, SW acting on delta W doesn't change. So this is equal to this. But this is equal to, by definition, as you are objecting, I should maybe have written delta W to the power of on the other side, but never mind for a minute. Okay. And let me write it like this. I'm trying to fix this problem maybe by Monday or so. So this is equal to this. And likewise here, the JW is unitary, anti-unitary. So the two JWs will cancel, but I'll flip the positions. So this is equal to delta W to the power half psi W, delta W, then delta W to the power minus half delta W prime. This is flipping. Because in the flipping, this will cancel. And now delta W to the power half is central join. It's coming from exponential minus 5k1. K1 is a central joint operator because the representation of the boundary group is unitary and K1 is one of the generators. So this is a central joint operator, central joint operator. So I can push out the two cancel. So I find this is equal to this. Okay. So what I have done, I flipped the positions of theta with theta. So this says that this object here is real. The scalar product is real. So what the end result is that imaginary part here vanishes. So you find that this product is simply the sum will come in. So I have proved causality. So this appears to be a very remarkable theorem where the Tomita operator is giving you causality. This kind of proof, as you can see immediately, will go through. For any, it doesn't need boundary group or anything, but you need the correct. And this kind of proof will go through whenever you apply this J and pick real surfaces. You have an interpretation in terms of causality. You will need some geometrical structure on which the group is acting. If it is not there, if you get this kind of commutativity, maybe there are problems in how to interpret them. So that may require some further work. So this is the proof. Causality is maintained. So let me show you what I want to do next. Okay. So I have now quantified this while operator. I have given how it acts in the entire Hilbert space. Okay. So it is about 1 hour. I just make two remarks. Next time I will make some. Okay. Let me make one remark. I have the Tomita operator is unique. Okay. The moment I give you the algebra and the cyclic separating vector, the Tomita operator is unique. So here I have given you the vacuum and looked at the algebra in the real ways. Then the Tomita operator I wrote down is unique. I know what it is. I found one, so it is the correct one. There is only one. Okay. And this polarity compensation is giving you causality. We will later, that is also giving you things that you will notice that the two wide algebras are commuting, not anti-commuting. So somehow, full statistics theorem is also embedded here, but I am not using for it. So this is worth remembering. And here I am saying that
Computing itself, very often computing, that was only because we were talking about goes on.
yeah, what I assumed is 2 by represented plus. We don't know that 2 by represented in plus one means that the fields obey that both places. That is the thin sentence theorem, right? Then thin sentence theorem is connecting the representation theorem. There is a big loop.
The same way, the same good point. The scheme of
You will get a different structure because of the fact that, as I told you, the reason is purely from representation in daily facts. I use the fact that the pi rotation is square 1. Okay. But if you are dealing with 2 half, it will be -1. So I make changes in the calculation as you go along. Then you will end up by finding appropriately defined while algebra they have used that they anti-commute. You also get that result automatically, and we will see how that happens. They call it the twisted Tomita operator is called. So I come to that. So there is a change that happens, which is foundational, coming from the fact that SU2 and SO3 are not the same. They are different groups because of the fact that SU2 is Z2. SO3 is a coordinate SU2 by Z. So that makes a difference. So I'll come to that later. I come up not trivial, and here I am simply saying that somebody else finds some other Tomita operator the same as this one. If the algebra I am looking at the policy, it is the same as. So this construction again is very nice because the quantization does not depend upon whether you represent the field to the particle by say running the finger or some other field. There's already a spin through that I whole bunch of fields that I got doesn't care. You get only one quantum theory from there. So the ambiguities that can in the quantum field theory context are mitigated or apparently gone. So I come back. Yeah, this is something to remember. Then I will. This is. Okay. There is also a. Foundation result, I would say. Namely, suppose I take the right privilege. These are remarks which I will not develop very much further. You have this unitary operator, exponential I T KW. But KW is characteristic of the regular wedge. One of the deep theorems of computer Takesaki is that this operator generates an outer automorphism for the algebra. That is, we know that because geometrically in the regular wedge, it represents a constantly accelerating particle in the regular wedge. So it doesn't lead it. Theorem of Tomita says that this is actually an outer automorphism. That is, we conjugate it, we get the same algebra. But if you go to the depth regular wedge, this KW is not the same. There is still a KW prime, everywhere. Depth right regular wedge should be careful. Happen here the same KW, but if you take the constant diamond, which will come, there is another K correct for constant diamond. They have discussed next time. We not this. But again, for the algebra in the constant diamond, it will generate an outer automorphism. In fact, if you go on taking the constant diamonds, intersecting them, each intersection and each union will have a different K and different unitary group like this. All of which will be generating outer automorphism. They look very strongly to me like some kind of a game, because each local region you have a transformation which preserves the algebraic structure. They are all different, but they are all local. What is it? How do they combine? So far as I know, the answer is not known. It looks like some emergent gate symmetry purely from quadratic theory. But what are the implications? What are they? That even that is not known. I think that it is something.
It's more like a connection. The modular base connection that is called.
It's not a connection. So it's outer automorphism of each other. Transport in them is different. It's called transportable endomorphisms. That is that transport. You can think of as a connection. That was done by such Hagen rovers, and they're called transportable endomorphisms. At that time, I tell you. So they did something fantastic. Namely, they did the local algebras and they found operators. They don't use words. You have to find operators to do one and two. They found the operators, they move them around from one local region to another local region. They maintaining its algebraic properties. Okay. So they actually move, and from there they proved the great group. They proved all kinds of other things. So that can be maybe translated in the language of connection. They don't use that language, but I suppose you can translate. Not this. If you don't even know what it is, existence. Okay? So somehow this is going beyond our standard understanding of quantum Roberto Longo wrote a long paper where he found out what is K is from a constant diamond. So he looked at the conformally invariant theory of dimensions and he made a conformal transformation from the relative to the diamond, checked that all the activities you are doing is mathematically correct, and he wrote out the operator. It is given in Hart's book. Can I understand what it is? I don't know what it is. It is some complicated expression there. Can do that. But what is it? What does it do? This is what it's not an accelerating factor. So what is it? I don't know. So we are hit with some new problem in this part. I think it is worth thinking about. There are many, which, in my opinion, many rich things are happening here. So, my personal attraction is the amount of fantasy that is going in here. It is telling that quantum field theory is not just writing Lagrangians and doing some stuff with functions. It is not that. There is something much deeper going on. And these investigations seem to be exposing this depth slowly. There are many things to be understood. Conceptually, even algebraically, there are many things to be understood. And My personal attraction is that it is very, very beautiful. Math is very beautiful. And the results that are coming out are also very, very impressive. Today I saw it within paper, it within and Stromeyer papers on this tubular, uh, what's it called? Time like tube theorem of borders, which I knew, but again, it writes nicely. So it's something very surprising. It says that if you take along this accelerating particle length, make it little thick, so that the guy who is accelerating the little patch, he will have access to the entire information on the entire universe. This is the theorem of Buffet's. How Buffett talked about this theorem, I have no idea. But this is the theorem of Buffett. And these people expose it using hyperbolic geometry, basically hyperbolic geometry. And our friend here was asking me a question from hyperbolic geometry. So by way of
That was originally the idea of Araki. Araki gave an order for this theorem in hyperbolic. And that is what has been carried
I see.
in without space time by Witten and
Yes. They are all related to this. This hyperbolicity. So what is the domain dependence, domain of region of influence? In that region, you have some analyticity property, this kind of thing. But what I was telling you is a warning. This hyperbolic geometry is very complicated. So, what is the story? About a few days ago, I saw this theorem. There is a proof now that curved black holes under slow rotations are stable. Why is it important? Speculation is that the world will end up with a bunch of curved black holes. In how many years? Who told me this? That somebody said it is some several billion years ago, and the student asked, really, so many, or it won't happen sooner, in a million years? And the speaker said, no, you take me. The student said, I'm happy. So, this paper is a mere 2000 pages long. Mere 2000 pages. So you can go and read it. This heavy hyperbolic, nonlinear hyperbolic equations, and this, these guys have analyzed it over a period of time in installments of 600 pages, small pages. So, for interested in hyperbolic geometry, you can go and. So, the moment you write this IgG, the D'Alembert's equation, which is appropriate to be scaled, okay? That has properties which cannot be easily comprehended, especially when it is nonlinear. All these things, Hadamard says, all these things, they come in that context. Okay, so next time I want to see how do I characterize these operators in the real space, in the Hilbert space. And we will see, that's what I will prove to you next time, that we will see that the operators which are localized in the real edge. So the Fourier have certain analyticity properties, and I motivate these analyticity properties, and we will see that this is strikingly similar. In fact, they are same as the analyticity properties we use in thermal field theory, in KMS states, in the Gibbs state. When we write the Gibbs state, expression minus beta t times something, we normally say that in time I can make P can make complex, and I can pick it with some strip. How does that happen? We will prove that it is coming because of this it is because of this localization. And later we prove that all these local algebras are the vacuum on all these local algebras are KMS states. So all these things have such analyticity properties. They are all thermal states in the language of StatNet. What do they imply? We will discuss later. So I think I'll stop here. And we'll continue next Monday.
just as a side note, what you call model and analysis, what the ICT
As what they call?
your last page, you have a statement of what is modular Hamiltonian. That is exactly what, that is exactly the context the ICT is also using for modular Hamiltonian.
I'm unhappy for that.
You are also using it, that's what I'm saying.
I will not use it as a Hamiltonian at all, ever.
You have better,
That's a language.
that is also a language.
Okay, there is no problem. If you want, it's a bad habit. I should eliminate it. It's not, because it's not a Hamiltonian. If the by Hamiltonian we mean real time evolution, then this K is not a Hamiltonian. It cannot. We mean that is it really evolving things from initial data? Answer is no.
You can write an operator, you can exponentiate it and write evolve it as a unit, right? That's the sense in which they are using it.
It's okay. Then I'm okay with it.
You have written here the model.
Because I copied it from somewhere. I must have copied it from. So it must be a bad habit which has come into the picture. I must be copying from nowhere. So it must be a habit which has got into the literature, which is highly misleading. It's because it is not a Hamiltonian in the physical sense.